So today we're going to be covering section 1.4 of the book, which is called Projections and Minimum Distance. So the new language for today's lecture is the projection of the vector y onto the vector x and the projection of the vector y perpendicular to the vector x. And using this concept, we will do things like compute the minimum distance between two planes or the minimum distance between a point in a plane and that type of thing. So this is going to be a continuation of our friend, the dot product. So let me remind you of the dot product given two vectors in Rn. We have the dot product that the dot product of the two vectors is equal to the sum of the coordinates of the components, the product of the components. So I equals 1 to n, xi, yi. So this is a real number. The dot product takes two vectors and gives you a real number. And because any two vectors in Rn span a plane, if you look just within the plane spanned by the two vectors, you can apply the law of cosines. And the law of cosines, once you unwrap it, allows us to relate the dot product between the two vectors to the length of the first vector, the length of the second vector, and the angle between them. So the law of cosines applies for vectors in Rn. And using the law of cosines, you get that the dot product is equal to the length of the vector y times the length of the vector x times cos theta, where theta is the angle between the two vectors once you put them in a plane, once you consider them within the plane that they live in. Now, for physical problems, and for other problems sometimes, you might want to get the projection of a vector onto another vector. So if you have some airplane and it's traveling with a certain speed, and it's flying from whatever, Toronto to New York, and there's an underlying airspeed behind it, or the wind it's flying through has its own speed. You might want to know the component of y that is in the direction, the component of the wind speed that is in the direction of the airplane, or the airplane's velocity, how much of that velocity is within the direction of the wind speed. If you have forces, you might want to know of the frictional force, what component is in the direction of gravity and what component is perpendicular to gravity and that type of thing. So what we want to do today is learn how to find, given a vector, find its projection onto another vector, find its component perpendicular to that vector, and see how that works. So I'll give you two different derivations for this. So here, I'm going to draw it in the plane, because ultimately any two vectors are in a plane. So here are two vectors. Here's the vector y. Here is some vector x. And I would like to find this vector. So that's a right angle. And I would like to find this thing, which I will call the projection onto the vector x of the vector y. That's the thing I would like to find. So I have a direction given by x. I'm trying to find this. So to find this vector, I need its length, and I need that it's, and I need its direction. X gives me a direction. I'm looking for a vector which is collinear with x. So x is giving me a direction. Here, what I need is this length. Because to figure out the projection of y onto x, I need length, that length, and I need a direction. So from little x, I can get the direction for sure. But I need this length. So that is a trig problem. This is an angle, theta. And so from trig, the length of this vector I want, projection x, y, is, so we're looking at trig. We're looking at SOHCAHTOA, right? So if you knew this angle, and if you knew this hypotenuse length, could you get this length? Yes. So I know that the length of projection onto x of y is equal to length of hypotenuse times what? Cosine theta. Now, the length of the hypotenuse, I've been given a vector y, right? My vector y is right here. So what is the length of the hypotenuse? It's the length of y. So here I've drawn it as if cosine theta is, I've drawn it for theta being an acute angle. Cosine theta is positive. That's why I can say the length of the projection of y onto x. Okay, super. Now, in principle, if I give you two vectors, do you feel comfortable putting them in a plane and computing the angle? Or is there some fast way to get that cosine theta? Use the dot product. The dot product has the absolute value, has the length of y times cos theta. So this thing is precisely y dot x divided by magnitude of x, length of x. Okay, so we've got one out of two things that we need. To get this vector, we need its length and we need its direction. So we've got its length. Direction of the projection onto x of y. So here I have to be careful. What I'm looking for is, ultimately, I'm going to say that the projection onto x of y is equal to the length of the ultimately what I'm going to do is I'm going to say that it's equal to the length So that was y dot x over the length of x. So that was the length. Times some vector. This vector, what should its length be? 1. If this vector is of length 2, then the length of this thing would be this number times 2, which isn't what it should be. So this thing needs to have length 1. Must have length 1 and be in the correct direction. So the correct direction is given by which vector, x or y? X. So I just need this to be y dot x over length of x. This is giving me the correct length. And then I need a vector which has the direction of x and is of length 1. So that would be x divided by what? Its length. So we've just derived the projection of y onto x. Projection of the vector y onto x is y dot x divided by x dot x times the vector x. I wrote x dot x because the length squared is the dot product. So this is a number. This is the vector. So let's do an example. As a reality test, we should do something like y is the vector -3, 2, and x is the vector 2, 0. So here is the vector x. And here is the vector y. And if I project y onto this line, I get this. And so if there's any justice in the world, well, that's an overstatement. That's what would you really hope that the projection of that particular vector onto that particular direction is? You would really like it to be -3, 0. Right? So let's just check. From the definition, the projection of I'll keep with the book's notation, the projection of y onto x is the dot product of -3, 2 with the dot product of 2, 0 divided by 2, 0 dot producted itself. And that is in the direction that is multiplied by the vector 2, 0. So the numerator is -6 plus 0. The denominator is 4 plus 0. And this is multiplying 2, 0. And that is -3, 0. So you see that projections, the derivation I gave you, I did the case where this angle is less than theta. If the angle is greater than theta, I could redo that derivation slowly and carefully, but it would work. It's just a trig thing. Are there questions? Okay, now, here, I got that vector. If I wanted this vector, this is the thing that we call perp yx. It's the part which is orthogonal to x. If you've got this and you've got this, how would you get this? So you started with y. You built this vector. Using those two, how would you get that vector? Sorry, what? Do I need to do more dot products, or can I just do vector addition? I should be able to get it by vector addition. So the perpendicular part plus the projection should give me the original vector, because this is the projection, that's the perp. And so that tells me that the perpendicular part is equal to y minus the projection That's true in general. So that's in general. For my specific example, I have that the perpendicular part is equal to minus 3, 2, minus 3, 0. We computed this puppy using all the dot product and stuff. And that is equal to what? 0, 2. And that makes us happy, because if I had done this on the first day of class, you would have said that this vector is the sum of the vector minus 3, 0 and the vector 0, 2. So if you are given a vector y and you want to project it onto x, you can do that with dot products. If you want to get the perpendicular component, you just subtract the projection from the original vector and you get the perpendicular component. So an example. Determine the projection onto V of U and the perpendicular, I should get the language right, the projection of y, the projection of U that is perpendicular to V. So this is the projection of U onto V, and this is the projection of U that is perpendicular to V. And we're given the specific vectors. V is minus 1, 2, 1, minus 3. And U is 2, minus 1, 2, 1. So the first thing is we compute the projection. The projection onto V of U is U dot V divided by V dot V times which vector? V or U? V, because we're trying to project onto V. So that is minus 2, plus 2, minus 3, divided by 1 plus 4 plus 1 plus 9 times the vector minus 1, 2, 1, minus 3. Yes?
So why is the bottom of the function both vectors?
Sorry, what?
Like why is the bottom of the
because this was the remnant of, this was the length of V, and this was V divided by its length to get a unit vector. And so the product of, I'm using the fact that V squared, the length of V squared is simply V dot V. Or another way of putting it is if I'd made the denominator U dot V, then the numerator and the denominator would have canceled. So this is minus 2 plus, so that's minus 5 over 15, minus 1, 2, 1, minus 3. And then the perpendicular part is simply U minus the projection so that is 2 minus 1, 2, 1 minus 1/3 minus 1, 2, 1, minus 3, which, when you do it, gives you 5/3 minus 1/3, 7/3, 0. So now we can check to see if we made any mistakes. So what are some checks? So the first check is the projection onto V of U parallel to V? That's the easiest check. This thing, is it parallel to V? Yes, because it's just a scalar multiple. The next thing we can check is the projection onto V of U perpendicular to the projection onto the perpendicular part? Because we were supposed to be getting this and then that. So that's the projection onto the perpendicular. So to check that, we would need to do what? How do you check things are orthogonal? Dot product. So that's the dot product of minus 1/3, minus 1, 2, 1, minus 3, dot producted with 5/3, minus 1/3, 7/3, 0. So that gives me minus 5, minus 2 is minus 7, plus 7, all divided by 3. And the final check is, does the projection of U onto V plus the projection onto the perpendicular part, if I've done this correctly, what is this sum going to equal? U. So that would be the sum of these things, so minus 1/3, minus 1, 2, 1, minus 1/3, plus 5/3 minus 1/3, 7/3, 0. So here we have 1/3 plus 5/3 is 6/3, which is affectionately known as 2. Minus 2/3 minus 1/3 is minus 3/3, also known as minus 1. Minus 1/3 plus 7/3 is 6/3, also known as 2. Minus 1/3 times 3 is 1. Yes? Okay. So no mistakes. Okay, let me give you another derivation of the projection, because there are two ways of deriving it, and if you don't like geometry, you might like the other way. Okay, so let's draw the picture again. So here is y, here is x, and we're looking for some vector. We seek a vector that is collinear with x such that, okay, so this vector, we're looking for a vector so that this thing is a right angle. What that means is we want y minus the projection onto x of y. If this is a right angle, then y minus the projection of x onto y should be orthogonal to x. So this thing is, if I took this vector and I just multiplied it by some number, and I didn't get a right angle here, this vector is too short. This angle is larger than 90 degrees. If I computed y minus this vector, I would get a vector which was not perpendicular to x. If I took the vector x to be, if I multiplied x by something too large, then when I computed y minus this vector, I would get a new vector which is not perpendicular to x. I'm seeking some multiple of the vector x so that when I compute y minus x, I get a right angle. So the projection onto x of y is equal to lambda x, where we've chosen lambda so that the vector I'm projecting is orthogonal to x. We're trying to choose lambda just right. Here, all I'm saying is that the projection of y onto x is collinear with x. I'm just saying it's some scalar multiple of the vector x. Here, I'm saying it's a very specific scalar multiple. It's the scalar multiple so that if I take y and I subtract off the projection, I get a vector which is orthogonal to x. So that means I want lambda so that y minus lambda x dot producted with x equals what? 0. So let's run with that. So I want lambda so that y dot x minus lambda times x dot x equals 0. I want y dot x equals lambda times x dot x. So that means if x is not the 0 vector, then lambda is equal to y dot x divided by x dot x. And I have just figured out that the projection onto x of y is equal to y dot x divided by x dot x times the vector x. Because I figured out what lambda is. So the projection is collinear with the vector x, and this is the multiplier. So I don't know which derivation you like better. Both are correct. Both lead to the same formula. Here, in general, you don't project onto the 0 vector. Everything falls apart if you try to project onto the 0 vector. Don't try it. So let's do another example. Okay. So, example. Find the distance from the point Q, which has Cartesian coordinates 2, minus 3, minus 1, to the plane given by 2 times x1 minus 3 times x2 minus 5 times x3 equals 7. So we have some plane in 3 space, and we have a point. So here's the point Q, here's the plane, and we're trying to find the distance. Now, certainly if you draw the distance, the distance is that's going to be a right angle. That little segment is going to intersect the plane in a right angle. If it didn't intersect in a right angle, then the point in the plane, that length can always be made shorter by moving my thumb until it's perpendicular. So the minimum distance is going to be when it's perpendicular. This plane, does it go through the origin? What would the right-hand side have to be for the plane to go through the origin? 0. Okay, this plane does not go through the origin. Okay, so we look at this and it makes our head hurt. So what we do is we try to figure out what to do if we had a simpler problem, which was instead of being in R3 and having a plane, if we were in R2 and we had a line. So let's back off and see how would we approach this problem if we were in R2. So we're going to look at the baby problem. We're in R2. We have some line. And we have some point Q. So certainly we have a position vector for Q. And if we had a point on the line, we would have a position vector for the point on the line. Really, what we're trying to get our hands on is this distance. That's what we're trying to get our hands on. What is the length of this? We have a line. It has a normal vector. This certainly has to be the projection of something onto the normal vector, that length, but the projection of what? I need a vector whose projection onto the normal vector is this. So the normal vector we have because we were given the formula for the line. The vector q we've got because we were given a point. We have a line, so in principle we have infinitely many points on the line. We need a vector whose projection onto the normal will be this. Sorry, what?
You can use this equation and this one.
That will give me.
Line
So I'm backing off on this problem. I'm just trying to do this problem in R2. So I haven't actually given you an equation for the line. I'm just drawing pretty pictures. So what could be a vector whose projection onto the normal would be this? Q minus P, P minus Q. What were you going to say? So this is the big idea. The big idea is I was given Q. I can find P by just finding some point on the line. And if I ask for P minus Q or Q minus P, that's going to give me this vector. So this vector, that's the vector P minus Q. If I take that vector and I project it onto the normal, P minus Q projected onto the normal will give me a vector whose length is the distance I need. Now, what's kind of mind-bending about this is each person in the class could choose a different point on the line. So like, everybody's got the same Q. One student in the class might choose this point on the line. That would give them this vector. But when they project that vector onto the normal, it's going to be this vector. And a different student in the class might choose this point on the line, resulting in this vector connecting Q and P. When they project that vector onto the normal, they're going to get this. So every person in the class could start with a different point on the line. They will get a different vector here, but when they project onto the normal, everybody will get the same thing. They'll get different projections onto the line because this student would get that, this student would get that, this student would get that. The projection onto the line would be different for each student, but the projection onto the normal would be the same for each student. So here what I've been doing in the problem solving is I started with a problem in R3 that was giving me a headache, and I backed off and went down to the problem in R2. The analog of a plane in R3 is a line in R2. A point in R3 is a point in R2. I figure out what to do in R2, and now I go up to the problem in R3. Are you with me? Okay, so we just need to do this for that particular problem. Okay, so step 1, find a point P in the plane. So can someone give me the Cartesian coordinates of a point which is in that plane? 1, 0, -1. Cute. So P is 1, 0, -1. This is a nice point because it doesn't have any fractions. And whoever came up with that point was thinking through that process of how to blend a 2 and a 5 to get a 7. And that's a very nice point. Other nice points, maybe not so nice, would have been 7 halves, 0, 0. Another easy low-hanging point would be 0, -7 thirds, 0. Another low-hanging point would have been 0, 0, -5 thirds. Those are all easy to get points. This is a very elegant one. So let's go with elegance. So we have a point in the plane. So now this has position vector. So the position vector is the vector that goes from the origin to the point. So the position vector P is 1, 0, -1. So step 2, compute Q minus P or P minus Q, it really doesn't matter, and project onto the normal direction. So P minus Q is 1, 0, -1, minus 2 minus 3, 1. Minus 1 is 1 minus 2 is -1, 3, 0. What is the normal vector for the plane? 2, -3, -5. And so the projection onto the normal of P minus Q is equal to the dot product of these two. So -1, 3, 0, dot product 2 minus 3 minus 5, divided by 2 minus 3 minus 5, dot product 2 minus 3 minus 5, times the vector 2 minus 3 minus 5. So that is -2 minus 9 is -10. 4 plus 9 is 13, plus 25 is 38, times 2 minus 3 minus 5. So at this point, what we've done, is this is P minus Q, and we have projected P minus Q onto the normal. So we have computed this vector. So now, step 4, Step 3, thank you, is compute the length. So that gives us 10 over 38 times the square root of 4 plus 9 plus 25. So that is 5 over 19 times the square root of, I feel like we've done this before, that's 38. At this point, you can stop. Yes? Negative 11. Minus, yes, it should. That's a pity. Not really a pity. There we go. That's life. No simplifying fractions there. So that is 11 over 38. And so that is, for me, I'm perfectly happy if you stop here. If you don't feel like stopping here, you can write 11 over root 38. Okay, so are there questions? Yes?
How do you get those points again?
Sorry, how did I get what? The first point, P, by inspection. By inspection. So you were given this plane. So the question was, where did the point P come from in step 1? So you're looking for a point that is on this plane. The easiest point to find is to set this to 0, that to 0, and then you get 7/2. Or set this to 0, that to 0, and you get 0 minus 7/3, and so on. That point was found by a classmate who realized that 2 and 5 make 7, and they put a -1 in. And that person was just saying, I like integers. Can I find something that doesn't involve a fraction? But every person in the class could have a different P and ultimately get the same answer. And ultimately, they must get the same answer. It doesn't matter.